So just to summarize a little bit, my main message is just to motivate that there are some things that can be learned by looking at the classical radiation reaction problem and the analysis of cell forces that can be useful and have some very clear analogies in QFT and curved spacetimes. The main one being the relation between Unruh effect and the radiation of charges in RINDLER spacetimes. So I'm gonna revisit very briefly the classical debate and analyze some arguments both for and against the radiation in charges in different situations. But then I'm going to focus more on the analysis of the cell force and the apparent paradoxes that happen there, and in particular, why we believe that once one moves beyond the point particle limit and considers extended bodies, it's much more natural to not consider uniformly accelerating charges, but in fact considering charges that have a micro-oscillatory structure in their motion, which also has a very nice analogy and with what is found in QFT results. So this is the first picture that I want to draw here. On the left-hand side, we have the usual picture that one has in mind when thinking about the Unruh effect, which is a rocket that is with some constant acceleration, and that inside we place a detector. And this detector, because it's in constant acceleration, will detect a thermal bath with a temperature that is related to the acceleration. This is more or less dual to the picture on the right-hand side. The black surface can be any sort of gravitational mass, be it a black hole, be it a mass, where we consider that the charge that is being held by that rocket at a fixed position is close enough so that we can discard all of the curvature effects. In principle, one could consider the curvature effects too, but they make things a little bit more messy. So if we want to have the analogy as clear as possible, we can just discard the curvature effects so that the spacetime in the right-hand side is also flat, and basically can be described in RINDLER coordinates and corresponds to the RINDLER wedge of that spacetime. So one possible analogy would be to consider a charge that is fixed at some distance from this gravitational source and an observer, this radio in this case, that is in free fall. Therefore, in analogy to the positive answer to the Unruh case, this radio here would detect radiation. As I said before, the previous talk has described very well how to analyze this calculation very carefully, so I'm not going to stop here very much. But this analogy and this moving forward with these two cases is something that is good to have in mind, in particular the relation between uniformly accelerating charges and charges being restrained from falling to a gravitational well. So let's start by just revisiting the most simple question. If we have a uniformly accelerating charge in Minkowski spacetime, does it emit radiation or not? On the positive side of the arguments, we have that one can just calculate directly and obtain Larmore's formula where the power radiated is proportional to the square of the acceleration. Therefore, if the acceleration is not zero, there will be some radiation. However, early on in the literature, there were some arguments against this. And just to mention a few of them, one can see that, for example, Maxwell's equations are conformally invariant, and we can take a uniformly accelerating charge to a static charge, to a stationary charge by a conformal transformation. Therefore, their fields should also be related by a conformal transformation, and then radiation would not be present. The answer to this apparent paradox would be that the conformal transform version of the fields for a static particle, if one takes the conformal transformation that particle to be uniformly accelerating, would not be the retarded solution, but would be this combination of one half the retarded solution plus the advanced solution, which in fact does not have radiation. However, when we try to analyze this problem, we want to look at the retarded solution, which would be breaking conformal symmetry in this case. A more subtle argument is that of the vanishing of the cell force. If we want to study what is the dynamical reaction of the radiation on the trajectory of the particle, we obtain, in the most simple scenario, this formula here, where the cell force is proportional to the derivative of the acceleration. Therefore, in regimes of uniform acceleration, the cell force would actually be zero. That is, we have a particle, and if we consider a wall tube around that particle, there is some energy that is being emitted away, but there is no dynamical reaction to that emission of energy, which in principle sounds weird. However, the self force is an object that is constructed locally. One just analyzes how the trajectory of the particle is modified by the fields that the same particle is emitting. But if we want to analyze the radiation, then we are having some knowledge about either a preferred observer, that is our detector, or if we put our observer in infinity, our asymptotic structure of the spacetime. So it's not that clear that we can make the argument that a vanishing self force should imply a vanishing radiation. I'm not saying that they should be unrelated, but that it's not immediately clear. Now let's move to the case of a RINDLER charge. That again can be seen just as a charge that is sitting on your desktop. It's being restrained from falling to the earth. So it's with respect to an inertial observer, it would be with a constant acceleration. The question here on whether this charge emits radiation or not is ill-posed because we have to specify with respect to which observer. And again, I'm not going to review the calculation, but if we consider a co-accelerating observer, that would be, for example, me looking at my phone here sitting on the table, I would not perceive any radiation because I am co-accelerating with the charge. However, if we consider an inertial observer that is in free fall, and this would be the more dual case to the Unruh effect, then we would measure some radiation. There is a nice way of viewing this that does not need to go exactly, although it's somewhat equivalent to defining Poynting vectors or energy fluxes of observers, and is by constructing the stress energy tensor associated to the fields of the charge that is emitting, and finding a way of splitting that stress energy tensor into a local part and a radiation part. If one tries to do this splitting basically by requiring that the radiation part, for example, has a source at the trajectory of the particle that is related to this radiation rate, then one will obtain that the splitting that is done by different observers is actually different. Therefore, there is not a unique way of ascribe a local field or a radiation field to a charge. And in any given situation, if one wants to do this splitting and defines what is the local field and what is the radiation field, one needs to introduce some additional structure, be it an observer or be it again an asymptotic structure. What is interesting to me is that this shares some similarities with the definition of a particle in QFT, in curved spacetimes. If one sees, for example, the local fields as a vacuum state, basically, one can think that you can have, for two different observers, two situations, one in which you just have local fields, that is, you just have a vacuum state, and one in which you have a local field and some radiation field, which can be seen as some measuring some excitations or some number of particles. And in that sense, the analogy between this classical radiation reaction problem and the discrepancies and subtleties in defining the radiation are already present here and are very similar to the subtleties that are present in order to define a number of particles in QFT, in curved spacetimes. However, I want to focus a little bit more now on the self-force analysis, because as I said before, we still have something weird happening. So we have that if a charge is uniformly accelerating, then that charge is losing energy. But at the same time, that charge is not reacting. Its motion is not being affected by this energy loss. There is a way of making sense of this energy balance, and it's by defining a concept called the acceleration energy, or the shot energy, that was introduced in some works by Rohrlich mainly. There is this quantity Q here, so that in periods of uniform acceleration, there is an acceleration energy that is negative and that is being accumulated in regions around the charge that somewhat compensates for the radiation energy that is emitted. In transient periods that connect these uniform acceleration periods with periods of inertial motion, this acceleration energy would be washed away. But in uniform acceleration, they would be the only compensation that one can find for the radiation. And again, one can understand this by doing yet another splitting of the stress energy tensor of the fields of the particle, this time making yet another splitting of the local part, where we separate on the one hand the solenoidal part of the stress energy tensor that will be divergence free everywhere. And we introduce this new part that can be seen as basically the part that is local of the fields, but at the same time is different from the Coulombian field of a particle at the same position, which will be divergence free everywhere. And at the particle, it will have a source that exactly compensates the source that the radiation term needs. That way, if we compute the energy associated to the radiation stress energy tensor, we obtain the radiation rate. And if we obtain the energy associated to the shot stress energy tensor, we obtain the acceleration energy, and we find some notion of energy balance. However, we have done a splitting of the stress energy tensor, and as mentioned before, this splitting will be observer dependent. Therefore, even though this gives us some kind of satisfactory conclusion to this passing observation about the cell force, there is still a feeling that we cannot do this in a completely objective and background independent way. We need some additional information about spacetime. This is what motivated us to look a little bit beyond uniform acceleration, and in particular thinking about what happens if one thinks not about point particles, but about extended bodies. So our toy model is just 2 point particles with equal masses and equal charges that are kept at a fixed proper distance. In order to have this condition, we need that both charges are accelerated with slightly different accelerations, which are basically given, can be seen if we put them a gravitational field and we place the particles at slightly different distances, then we obtain the conditions on how these two accelerations should be related to the distance between them. And what we analyzed in this model is what are the cell forces that each charge is exerting on each other. We have on the top formulas are the force that the tail particle is applying on the head particle and vice versa. And interestingly, we can combine them by basically assuming that they are acting on the same point and obtain a result that is what one would expect from the point particle analysis, that is a cell force that is a force that opposes the acceleration. It's not a friction, because when one talks about friction, one thinks of a force that opposes velocity, but it's in friction for the acceleration, where the term can be reabsorbed into the definition of the mass. This term is what usually is called the electrodynamic mass, that would have a divergence in the point particle limit. And would have some finite size effects, but for an extended body, this is perfectly well defined. And in this case, it can be understood that if we start with a particle in inertial motion and we tune some acceleration, then the cell forces will contribute to dress the mass of the particle with this electrodynamic contribution until it reaches the uniform acceleration, and this contribution is stable. However, if one tries to think how to actually get to this stationary state, starting from inertial motion, it seems that one would need that the rockets that are pushing the charge to accelerate it and get to this uniform acceleration have to be very precisely tuned to compensate exactly for this renormalization of the mass and for this cell force. So it feels that this is somewhat unnatural. On the other hand, we still have the problem that if we have long periods of uniform acceleration, or even perhaps an eternally uniformly accelerating charge, we are accumulating constantly these short negative energies. However, if instead of this, we consider a more natural hypothesis in which we try to accelerate the charges by applying a constant force or something like, or a switch-on function for the force, then we probably cannot compensate at the beginning for the electrodynamic mass contribution, and therefore we will overshoot or undershoot. And the charges will be forced to bounce a little bit and oscillate. And in fact, these oscillations help us to get away with this accumulation of the short negative energies, because they will compensate, they will fluctuate up and down, and we will still recover the classical results as the Larmor's formula that will hold on average. More interestingly, this proposal has a very clear analogy in quantum fields, because if one considers the quantum mechanical trajectory of a two-level detector in uniform acceleration, then one obtains that the result also includes this micro-oscillatory structure. So just to keep things brief and on time, I'm going to just summarize the main points of this brief talk. The first idea is that the concept of radiation shares some similarities with the concept of particle in a QFT in curved spacetimes, in the sense that we need some additional structure. We cannot define radiation globally for a given charge, but we have to define radiation with respect to one observer or with respect to an asymptotic structure of a spacetime. And in particular, different observers can disagree in whether they measure radiation or not, depending on what access, as Stephen Fulling was mentioning before, whether the observer has access to just the RINDLER wedge or the whole spacetime, for example. Moreover, what we can recover and get rid with this apparent paradox of the vanishing self force in uniform acceleration by constructing an energy balance based on a splitting of the stress energy tensor, but this can only be done for a given observer. And different observers will have a different way of constructing this energy balance. And finally, if one moves away from the point particle limit, the self force analysis suggests that the motion is not really uniform acceleration, that's only on average, but if one looks deeper, it has some kind of oscillation structure. This result holds in QFT in curved spacetime, but we were not able to prove it exactly and formally in the classical case. So this is, as of now, an open question, and I would be very interested in hear your suggestions about it. So thank you very much for all. I hope you found this interesting and waiting for questions.
Thank you, Jaime. So Antonio has a question. Antonio Ferreiro, please. No question? So probably it was, so there are no questions then?
I do have a question.
Okay, please go ahead.
Yeah. Congratulations on, and thank you for a talk that was nicely complementary to mine. You hit a lot of points that I didn't have time to talk about. But my question has to do with this observer dependence of the splitting. That went past a little fast for me. In what sense does the separation of the shot term from the other terms depend on the observer?
So, well, just take, for example, the case of a RINDLER charge for the co-accelerating observer and for an inertial observer that is in free fall. One observer will not have the radiation part. So there is no need to include a short term, because one doesn't have to compensate for the sources of the particle, because we don't need those sources because there is no radiation being emitted away for that observer. Whereas for the inertial observer that is actually measuring some radiation, one needs to be able to explain where does this radiation is coming from, and that is where the short term appears.
Well, how is this splitting defined? In Rohrlich's paper, it has nothing to do with with observers. It's entirely tensorial.
This splitting was done later by Rowe and some more people, I believe. Where what they are looking for is to basically kind of like modify a little bit the splitting by adding some delta sources that will actually have, like, the way the splitting is constructed is in order to have this property that the short term will basically give rise to the acceleration energy, and that will source at the particle the term that the source of the radiation part of the stress energy tensor needs. So it's basically a splitting that is done by adding and subtracting in a kind of subtle way some delta source contributions at the particle. So in that sense, it is at least not explicitly observer independent.
Okay.